Okay, well, thank you everyone for joining today's virtual Hyperledger meetup. Today we're talking about Secure Multi-Party Computation Lab. We have our speaker today, Hossein, apologies if I'm pronouncing this wrong, but Hossein Namazian, senior software engineer at Superlogic, and he will be talking about a new piece of code that will be coming soon to Hyperledger Lab. So with that, why don't you take it away, Hossein?
Thank you. Hello, everyone. I'm Hossein, and today I'm gonna propose our Secure Multi-Party Computation Lab. I'm senior software engineer at Superlogic, and thank you for attending to this meetup. So let's get started. And the agenda of this meeting would be first a very quick recap to ECDSA cryptography, which is the base basically is required to know a little bit about the ECDSA cryptography in order that then we can go more in depth through the MPC wallets. Then I'm gonna introduce some traditional wallets and their security issues. After that, I will introduce some MPC wallets, some of the most important MPC wallets in the markets. And basically, I'm gonna introduce three of them, which is MPC, VSS, and Lindell and CMP. And finally, I'm gonna propose our work at MPC Lab. So first of all, I'm gonna verify a little bit about the ECDSA cryptography. And before that, we need to know about what is ECDSA cryptography system. So ECDSA cryptography is based on elliptic curves with this formula. In fact, it is y2 equal to x3 plus ax plus b, and b are the coefficients that will be configured by ECDSA cryptography system. And here, for example, you can see a very simple elliptic curve. So you see some points on the curve. For example, C here is shown on the curve, and it's mirrored D on the other side of the curve. And if and then you can see the red line passing through C and D, but it doesn't meet the curve on the other points. So we define C plus D, a point addition. C plus D is equal to infinity. And also we have A and B on the curve. And if we find a line passing through A and B, and we see that the line is passing through C, and then it doesn't meet any other points on the curve. So we say that we define point addition, ECDSA point addition, A plus B plus C is equal to infinity. So if we combine these two terms, we see that we can conclude that A plus B is equal to D, because C is equal to negative D. So we can conclude that A plus B is D. So to sum it up, we can say that if we're gonna find the result of A plus B, we need to find a line passing through A and B, and it will intercept the curve on point C. And if we mirror the C to the other side of the curve, we can find D, and D is the result of A plus B. So this is the point addition that we define. And then consequently, we can define point multiplications. So let's say X is a scalar, and G is a point, and we're gonna find the multiplication of X to G. So X multiplied by G would be big X, and we can find the results by adding G to itself for X times, okay? So for X times, if we add G to itself, using this point addition that we introduced previously, we can find a new point, which is big X. And I should say that if we're gonna find G plus G, and let's say G is here, and we know how to add A and B when A and B are distinct points. But what about a point G that is going to add to itself? For this one, we should use the tangent line passing the curve at point G. And then it will, for example, let's say, meet the curve at this point, let's say P. And if we mirror the point at point R, it would be the result of G plus G. And then again, we repeat this process for X times. So these are the basics and fundamental point addition and point multiplications defined in the ECDSA cryptograph system. So for as I mentioned, we in the ECDSA cryptography system we have an elliptic curve in the form of y2 equal to x3 plus ax plus b. So a and b are the coefficients of the curve, and then we define a base point or generator point G and order n. And these two parameters are chosen in the such that n is a scalar. If n multiplied by G, the result would be infinity. So and n is a prime number. So we cannot choose any arbitrary number of G, any points on the curve as the base point. So basically it should be found in a brute force way. And so we have point G, and then we can have point 2G and point 3G. And finally, we reach to point NG, which is infinity. So 1, 2, 3, and n. After that, n plus 1G would be G, n plus 2G would be 2G, and again n plus n, which is 2n, G is again infinite. So that means that these points are repeated, and we say that G can generate a cyclic group. So this is basically the main feature of G, that it can construct a cyclic group. So after all, we say that private key is a random scalar between 1 and n, and as we said, is the order of the group. And the private key, the public key is the multiplication of the private key to the base point. So in order to generate the key pair, we first need to generate a random number between one and the group order. And then the public key would be the multiplication of the private key into the base point. So each ECDSA cryptography system, we have different types, we have different configurations of cryptography system based on the curve coefficients, the base point, and group order. So for example, I have put here the configurations of the K1 says 256 K1 ECDSA, which is used in the Bitcoin and EVM blockchains. Configurations here you see A parameter is 0, B is 7, and G point is mentioned here, and this is the group order. So the term AX is wiped out. So we have, so the curve is y2 equal to x3 plus 7. And we have also different configurations for R1 or any other variation of ECDSA. So till now we know how to create an ECDSA cryptography system, and then we know that how we can generate a key pair, but how can we sign a message? So let's say we have a message and we want to sign it by a private key D and using the private key D and its related public key, which is shown by Q. So the signature is computed in 3 steps. The first step is to choose a random number, and this K. So first of all, we generate a random number K, and then we multiply K by the public key Q, and we find R. And so we know that a signature is the combination of 2 parameters, R and S. And the R parameter is the X coordinate of R. So we show it by R of X. And the S parameter of the signature is K inverse multiplied by M, and M is the hash of the message plus R that's found in the previous step multiplied by the private key. So, the combination of R and S would be the signature. And in fact, the signature is consisting of 2 scalars, but in most cases you will see it in a serialized form. So what we have seen as a signature is in fact the serialization of R and S. So what the wallet is. So a wallet, in fact, is a system that is configured with an ECDSA cryptograph system with pre-configured parameters A, B as the curve coefficients, G as base point, and N as group order. And then a wallet is responsible to generate key pairs and store the key pairs securely, and also is responsible to sign messages or transactions. So yeah, the private key is a random scalar. Public key is calculated by Q equal to G multiplied by G, when G again is the base point. And we know that we cannot compute the private key from public key. So based on our current technology, it is impossible in a rational time to compute the private key from the public key. And we know that the security of the private key is very crucial, because if we lose our private key, in fact, we'll lose our assets. So in fact, the privacy of the security of our assets are bound to the security of the private key. So we have different types of wallets, traditional wallets. So we have web wallets, and we know some of them. Most famous web wallets are MetaMask and Coinbase. Mobile wallets like Trust Wallet or Coinomi. Desktop wallets like Exodus. Hardware wallets like Ledger Nano and Trezor Model T. Or also we have custodial wallets that are used by exchanges or enterprises or financial organizations, such as Binance, Coinbase, BitGo, etc. Also, we have multi-sig wallets like Gnosis, and we have a lot of wallets at the moment in the market. And the most important issue with this kind of wallets is that the entire security of the wallets and assets relies on the security of a single key. So that means that if for any reason like a breach or phishing or a wallet compromise or any other reason, if our private key exposed, then our assets will be easily stolen. And on the other hand, recovery of the key is limited to the seed phrases. So if for any reason you lose your seed phrases, you cannot recover your key. So it is required that you back up your seed phrases or private keys somewhere properly and securely. So we know that the wallets mentioned till now are some kind of prone to single point of failure, and they are not very secure. So the next generation of wallets are introduced as MPC wallets, so multi-party computation. And what do we mean by multi-party computation, and what are intended for? So they are supposed to be a distributed system that they generate key and store the private keys, and also they sign and they run the signing process in a distributed way. So there are several parties that are contributing together in order to generate the key, store them, and sign the messages. And it is supposed that none of the parties in an MPC network has the knowledge of the wallet private key. So that means that if a key is generated mutually by and with a number of parties, none of them knows any knowledge of the private key. So the entire knowledge of the private key is missing from the parties. And secondly, none of them is able to sign a message without the contribution of others. So that means that each party has a partial information of the key, the wallet key. And none of them can acquire the whole information of the private key. And none of them is able to sign a message without the contribution of others. And so if none of them has the whole information knowledge of the private key, how do they sign a message or transaction? The answer is that each party is partially signed the message. So in the end, we aggregate all of their parties' partial computation together in order to confirm the final result, which is the signature. So this is what we are intended from MPC wallets. And now I want to briefly discuss about three types of well-known MPC wallets. And the first one is based on secret sharing or verifiable secret sharing. In this type of MPC wallet, we have a party which is a kind of a dealer party that generates the private key, and we call it D. And then the party generates a polynomial of degree k, p of x, and it sets the private key as the constant value of the polynomial. So the polynomial of degree k is in the form of d plus a1x plus a2x2 until plus akxk. So we have k coefficients plus d as a constant value. So in total, we have k plus 1 unknowns. And okay, so the dealer party has generated this polynomial, but it doesn't share the coefficients with other parties. Let's say we have n parties in the MPC network. But on the other hand, from the Lagrange theory, we know that if from this polynomial we had k plus 1 points, then we can compute the polynomial. That means that the dealer is now generates n points out of the polynomial. So P1 is the P of x1, P2 is P of x2, and Pn is P of xn. And then each point will be shared with one party. So point P1 will be shared with party 1, P2 will be shared with party 2, and Pn will be shared with party n. So in the end, each party has only one point, okay? And so none of the party at the moment, except the dealer party, cannot compute the private key, and it is not able to sign a message by the private key because it only has only a share, only a point from this polynomial. So the question is, how can we sign a message by private key. So let's say a client is a client want to sign a message. So in this case, the client needs to retrieve k plus 1 points from the MPC networks, so the parties, and then reconstruct, in fact, the private key inside the system, and then sign a message. So the procedure is that we generate the key, generate the polynomial, and extract points k endpoints from the polynomial and share them across MPC network, and then the client should get the k plus 1 points from the MPC network and compute the private key, sign the message by private key, and that's it. So this is the process. This is how MPC VSS works. And so as we have seen, none of the parties can acquire the private key by its own share. And the system as a whole can tolerate a number of parties are lost or compromised. So we have n parties if at most n minus k minus one of the parties are lost. Still we have we can we have k plus 1 parties are working, so we can the MPC can work without those missing parties. So I think as we have seen, the algorithm is very easy to understand and implement, and the performance is very good. So it is very fast. But the problem with the VSS is that the private key is reconstructed by client each time to sign a message. So as you mentioned, whenever a client wants to sign a message, they need to fetch down k plus 1 shares from the network and reconstruct the private key and then sign a message. So it is to some extent good, but in most cases, it is not sufficient. And yeah, we are going to the next algorithm, which is based on Lindel's algorithm, which is published by Lindel, who is a cryptography scientist. And this algorithm is adopted by Coinbase Wallet as a Service. And the algorithm is based on two-party fast ECDSA signing algorithm. So it is limited to only 2 parties. And the wallet key is never generated and nor constructed. That means that through generation of the private key, the main wallet key is not itself is not generated. And whenever we are going to sign a message, we don't need to reconstruct the private key. So we have 2 parties, and both parties are required to participate in signing protocol. That means that if one of them lost or went down, the other party cannot sign the message. So it is a kind of 2 of 2 algorithm. In comparison to VSS, that it was k out of n. So in VSS, we had some kind of flexibility in the number of active parties that can produce the signature. But in the Lindel's algorithm, both parties must be contribute in the process to sign a message. By the way, the algorithm, as we will see, is almost easy to understand, and the performance is good, I think. And yeah, you can run it almost very fast. But as I mentioned, the problem with this algorithm is that it is restricted to the number of parties. So we should have only and only two parties. And for signing, we need both of them. So here, I'm gonna briefly explain how Linda's algorithm work. First of all, how do we generate the private key? So we have two parties, P1 and P2. In the first step, party 1 generates a random number as the private key. D1 and P2 generates D2, a random number as its share of the private key. Consequently, they can compute their public key, Q1, which is D1 to G, and Q2 is the public key of the party 2, which is the multiplication of D2 on the base point G. So we have D1 and D2, and the assumption is that the private key is the summation of D1 plus D2. So, and consequently, the public key is the summation of Q1 and Q2. So this is the first step. The second step is that each party shares its public key, not the private key. And the private key will be never exposed and shared with the other party. So each party receives the public key, and it is able to construct the wallet public key by adding both public keys, Q1 and Q2. And so, yeah, this is the entire process. It is very easy. So we generate the key and share it, and we construct the public key, and we don't need to understand the private key. And yeah, none of the parties share its private key, and the wallet key is never constructed. So how do we sign a message? So we remember that from yeah. We remember that we need to generate a random number, K, and multiply it to public key Q, and R, and the X coordinate of the R is the signature R parameter, and then multiplying the K inverse to M plus RD, which is R multiplied by private key, we can acquire the S parameter of the signature. So here, now we have two parties, P1 and P2, okay? Each party first generates a random K, K1 and K2. And we assume that the real K is the multiplication of K1 and K2. So this is the first step. The second step is that each party computes its R. So R1 would be K1 multiplied by Q, and R2 is K2 multiplied by public key, and we have the public key from the previous step in the key generation. So, and consequently, we can acquire the little r as the x coordinate of each big R. Okay. So we have R1 and R2 generated by party 1 and party 2, and then they share their computed R. So both of them has the information, the knowledge of R1 and R2. And then we know that R, the final R is K to G, and K is the multiplication of K1 and K2. And K1 to G is R1, so we can so R2 so the party 2 can compute R from K2 R1, and party 1 can compute R by K1 R2. Okay. So so till now, each party knows the R parameter of the signature. So what about the S parameter? Before we go further to the next step and computing the S parameter, there is a very important cryptography system that we need to know, and it is Payer crypto system. So Payer cryptography is, in fact, Payer key is the combination of a secret key and a public key. So each Payer key pair is has a secret and a public key. And the public key, so Payer feature has the feature that we can encode the message by public key, and a Payer secret key can decode the encoded message. That means that if we have message X, we can encrypt message X by the public key of Payer, and it would be X encoded. And again, we can decode the X encoded by the secret key, and again, we can retrieve the X. And the most important feature of the Payer cryptography system is the homographic cryptography. So that means that, for example, let's say we have X and Y, and relatively we can encode X and Y, and we have X encoded and Y encoded. So we encode X and Y by public key. Then we can compute the summation of X and Y encoded by adding X encoded to the Y encoded. So if we need X plus Y encoded, we need to compute the X encoded and Y encoded and add them together. Or if we're gonna compute X multiplied by Y encoded, we can encode X and Y and multiply both of them together. So this is the most important feature in the Payer cryptography system, and we are using this feature in the MPC wallets. So with the Payer cryptography, with the Payer key, we are using in the next step to compute S parameter of the signature. So each party has its own Payer key, and they share their Payer public key to each other, but they never expose their Payer secret key. So the first step would be one of the parties, let's say party 1, encode its private key X1, and shares this encoded private key to the other party. So it is good because the other party cannot get the information about party one private key. So party two has encoded X1, and party two is also able to compute X2 encoded by the public key. And finally, by adding these two together, we can compute the private key encoded. And we know that the private key is in fact the summation of X1 and X2. And after that, we can compute R, which is computed by in the previous step to X, and the encoded of Rx by multiplying encoded R to encoded X, and then encoded M plus Rx is the encoded M plus encoded Rx, and finally the encoded K2 inverse in M plus Rx can be computed easily using the Payoneer key. So let's say it is S2. So we have S2 encoded. So this is the partial computation done by party two, and it will share this S2 encoded with party one, and party one is able to decode this S2 encoded and get the K2 inverse to M plus Rx. And finally, by multiplying K1 inverse to S2, it can compute the signature as parameter. So it is not very hard, I think. The key concept in this algorithm is the Payoneer cryptography system. So as I mentioned here, we need two parties to contribute to each other to compute the signature. And we need exactly both of them. And none of the party can sign a message without the contribution of the other party. I mentioned the problem, the limitation with the MPC Lindel's algorithm, and it is the limitation of the algorithm to the number of parties. So MPC CMP algorithm, which is the most well-known algorithm, and it is used by Fireblocks at the moment, and it is in fact published by some scientists that the first character of their name has confirmed this CMP. And yeah, the CMP algorithm is inspired from GG20 algorithm, but some years ago, Fireblocks announced a severe algorithm level of issue in the GG20, and after that, the authors of GG20 also announced that this algorithm is obsolete and shouldn't be used because of the issue. So CMP has fixed this severe bug, and now it is, but it is when you read the paper, you can understand that it is completely inspired from GG20. So in fact, we can say that CMP or GG20, both of them, has combined VSS and Linde's algorithm to benefit both, and they are able to generate configurable K of n private key So we can have an MPC network of n parties, and each time that we're gonna sign a message, we only need k parties out of n. And again, in this algorithm, in contrary with the VSS, the wallet key is never generated nor constructed, the same as Linux. And yeah, however, the algorithm is very complex to understand and implement. And also it is not as fast as VSS and Linux. However, the key generation is very slow, but they have two kinds of signing algorithm. The regular signing algorithm is very slow, but they have a kind of pre-sign algorithm that you do some computation beforehand, and then you can use those pre-computed information each time to sign a message. And this pre-signing is very fast. So as fast as VSS or Linux. And here is some mathematics. So I think they are a little bit complex, but very fast. I'm gonna recap very quickly. So we have n parties. Each party generates a private key and consequently the public key. And then again, each of them will generate a polynomial from their private key share. So we have n polynomials. And again, from each polynomial, they extract n points. And they will share, each party will share 1 point with one party. So these points are shared with party 1. These shares will be shared with party 2, and these are shared with party n. And the assumption is that the wallet key is the summation of all private keys. The public key is the summation of all public keys. And the polynomial from this private key is the summation of all polynomials. And consequently, the shares that we extract from the main polynomial is the summation of all these partially computed polynomial shares. So each party is able to only compute its share from the polynomial and also the wallet public key. So none of the party has the knowledge of polynomial or the private key. And that's enough for the party to sign a message. So I think I have explained the algorithm for key generation. And the signing protocol is very complex, so I don't want to explain it in this meeting, but I will post the algorithm in simple words as a blog post in future for sure. Okay, so we have in fact verified different MPC wallets. So what is our MPC lab? So our MPC project is designed based on MPC CMP algorithm, and it is developed in Golang. And our lab is in fact consists of a Go library or package, and our library is here is the architecture of our MPC library. So we have MPC core library so that covers ECDSA, Paylor, El-Gamal, Pedersen, some zero knowledge blocks that are required in MPC protocols. And then we have the key stores. So we have in-memory key store, file system key store, database. So these types of key stores are not recommended for production for sure, but they are good enough for development. And we have vault key store, which is intended for production. And also we will have HSM key store, which will be used as the backend of the vault. So in fact, in production, we have vault key store with the backend with HSM as its backend. And in the next version, we will have vault plugins. So most of these core libraries will be integrated into the vault plugins. And on top of the cryptography core libraries and key store, we have CryptoSuite. And CryptoSuite is inspired from the Hyperledger Fabric SDK CryptoSuite. So the CryptoSuite is a piece of package or library that has combined the core library, core cryptographic library, and key store together in one place. And then on top of the CryptoSuite, we have MPC protocols. So MPC keygen, signing, pre-signing, backup, refresh, etc. So this is our MPC library architecture. And then apart from the library, we have MPC wallet node. Yeah, it is a wallet node that can in fact create a MPC network. So we have different MPC nodes that working together to conform an MPC network. And finally, we will have MPC wallet SDKs in Golang, Node, and Python that can be used for interacting with MPC nodes. And here is the architecture of MPC wallet node. So we have MPC core, that is in fact the MPC core library or core CryptoSuite library. And we have vault driver, database driver, and they are used for connecting to database or HashiCorp vaults. And yeah, they are used by MPC core as a plugin for in fact the key store. So we have metrics plugin that can be used for connecting to metrics server like Prometheus. We have events. That are used for event sourcing or streaming to message brokers, message queues like Kafka, Redis, or some other message brokers. Also, we have log management in the system. And at the moment, the logs are written to rotary files, but in future we will add some log management servers. And then network profile and config management are used by MPC core and other blocks in the system. And this network profile is very, very similar to what we have in Hyperledger Fabric as connection profile. And it is used by the gRPC server for peer discovery. And on top of gRPC server, we have gRPC stubs. And gRPC stubs are used, they are like APIs that are served to other MPC nodes. And also we have a gRPC HTTP reverse proxy that is used for interacting with MPC clients. So we have two gRPC servers. One gRPC server is used for connecting to MPC nodes, and the other gRPC server is used by the HTTP reverse proxy for interacting with the MPC clients. So the roadmap is that we are gonna release our first version in the April next month, and it will include MPC Go library package and MPC wallet node, and it is supposed to support ECDSA so 256K1, which is used for EVM and Bitcoin. So, and it will consist, it will include in-memory file system, database, and vaults, secrets, key store. And as I said, these three can be used for development, but they are not recommended for production. And this one will be used, is recommended to be used for production. And we will, in the first version, we're gonna propose the MPC Go SDK, as well as some Docker compose, and Terraform scripts for deployments. And for the next steps, you're gonna add ECDSA, EDDSA, and ECDSA R1 algorithms to the MPC, as well as so the first version will support MPC keygen and MPC signing, but in the next step we will release key refresh, and also we will support backup and retrieve algorithms. And the next release will have MPC Vault plugins, which is one of the most important part of our lab. So we can move the burdens of computation from the MPC server to the Vault plugins, and it would be much more secure than the current version. And finally, we add Node and Python to MPC SDKs. And it is not very in priority, but it will be good to have MPC CLI in future for interacting with MPC for deployment or interacting with the MPC nodes using the CLI. And that's it. Thank you very much. And questions?
Yeah, it looks like there's one question in the Zoom chat.
Yeah, so it says that uh, definitely need to listen to recording to better. Yeah, yeah, definitely. I think this recording will be posted to YouTube, and also I think after the first release, we will post some blogs for MPC algorithm. Is it a Hyperledger project?
One note about that, I
Ye-
just put a link to the recording in the Zoom chat. So if people want to find it, I'll also email it to everybody after this as well.
Yeah. And about the GitHub repo, it will be published in April. And in MPC VSS, the private key is generated every time a message needs to be signed. Is the private key generated each time different, like mixed with a counter or something? So in fact, hmm, sorry. In most of these algorithms, not only for VSS, also in Lindel's and CMP, the key refresh, we have a key refresh algorithm. So, for example, in Windows, we have D1 and D2. So after each signing, we add a random number alpha and minus random number to D2. So we generate a random number and add it to the D1 and we subtract it from D2. So it must be, so we must generate a new, we must refresh each private key such that the wallet keys are still the same as before. So we are not gonna change the private key, but we definitely changed the share private key. Yeah, in fact, VSS uh, is a is verifiable secret sharing, and it is, as you know, Shamir secret sharing is the most well-known secret sharing algorithm. But I have mentioned the algorithm here in a very simple words. But in production, we have verifiable secret sharing in order to make sure about the honesty of each party. So we need to know we need to make sure that each party is honest, and this is the reason that we are using verifiable secret sharing. So VSS has some more steps for that. But here is Shamir secret sharing algorithm, in fact. And yeah, we have more steps using some commitments like Pedersen or other kinds of commitments for verifying the honesty of each party. Yeah, definitely I will suggest references. So the best reference to each of them would be the papers. So for example, for Linda's we have uh, a, we have a paper named, I think, a two-party fast ECDSA signing algorithm, and for GG20, we have, if you search GG20 if you Google GG20, you can find the paper, and also if you search NPC CMP algorithm, you can find it. So yeah, I think the best resource would be their papers. But as I said, GG20 and CMP, both of them all are almost the same, except that CMP has fixed some problems. Yes, MPCCM Fireblocks has published C++ code of the CMP. Yeah, and we have used a lot from the open source resources.
Are there any other questions? And I'm not seeing any questions on YouTube. Oh, I see a couple more questions came in. Hussein, would you like to address the questions that just came in on the chat channel?
Yeah, I would like to ask, is this an official project from Linux Foundation of private, or yeah, it will be released in future. Any Discord channel? Not yet, but I think after the first version.
What I can do is when this has been released as a lab and when there is a Discord channel, I can email everybody who signed up to this meetup and share those details. Great. Any other questions? Well, if not, we certainly would look forward to continuing the discussion with you. As we were just saying, there will be a lab coming. There will be a chat channel where we can bring the discussions. You know, Hossein, you're certainly invited to do more meetups in the future. So for now, what I can do is I can send the recording to everybody who signed up. And if you share these slides with me, I can share the slides with everybody as well. And then we'll follow up with people soon when the lab and the channel is available. So those can be the immediate next steps. But if you have any questions in the meantime, certainly I think maybe reaching out to Hussein directly on LinkedIn may be a good next step. And then we will follow up with you again soon with more of a community channel when that becomes available. Yeah, and as I was just see a question came in about can you share the PowerPoint? Yeah, I was just saying that I will email everybody the presentation. Hussein, if you're able to share that with me, I will email it out to everybody.
Yeah,
And
for
thanks
sure.
for your time today, Hussein, and everybody else. Yeah, again, looking forward to continuing the discussion with you.
Thanks
Thanks,
so much,
everyone.
everybody. Bye bye.